Hi everyone, we are into chapter 5 on cloud development and precipitation, and a huge chapter, a very important chapter. And let's start with what you already know, and what you know is already important. So when I look at a meteogram such as this out of Morristown, New Jersey airport, I am looking at what is important to pilots. What's important to them is what you see right off the top. The clouds are important to them, and they're critical to pilots for navigation and for safety. They're looking at ceiling height, visibility, obstruction to vision, precipitation, and precipitation types. So these are all things that are right below temperature and dew point on their meteogram that they look over. It's important to them, it's important to us too. You already know, critical in meteorology, that warm air rises, expands, and cools, and then cold air sinks and contracts and warms. You already know all this. We're just going over expansional cooling, that a parcel of warm air could come off the ocean laden with water vapor, and it might be blown against a mountainside where it rises along the mountainside. As it rises, it expands in the lower atmospheric pressure, and as it expands in the lower atmospheric pressure, it is pushing its molecules along the walls of this imaginary parcel. As those molecules push along the walls of the imaginary parcel, they start to transfer their energy to the walls. They start to lose the energy within their own molecules as they transfer it to the walls. As the molecules have less energy to them, they have less heat to them, and the temperature of the parcel tends to drop. So a parcel of warm air rises, expands, and cools. In cooling, it might condense, and it might be forming rain on what's called the windward slope of the mountain. And that is analogous to our carburetor example. And our carburetor example says that warm air that's been fired up by a spark plug, that's what gave it the energy, rises and pushes against the piston, just like the walls of the parcel. As the warm air rises and pushes against the piston, it transfers its energy to the walls of the piston. Those molecules now have less energy. They start to cool, and when they cool as an expanded cooling parcel. Just to review again, compressional warming, that cool air moves over the mountain, and now it starts to get more dense as it's cool, and it starts to sink. As it sinks, it runs into higher atmospheric pressure down at this lower altitude. That higher atmospheric pressure pushes on the parcel to produce more forceful collisions of the molecules inside the parcel. They've got less space to move, so they are transferring energy from the walls of the parcel to the molecules themselves. The temperature of those molecules increases. That means that down in the valley, you have this imaginary parcel which is now smaller and warmer. You often see deserts, dry deserts, on the other leeward side of the mountain. If you look at this in terms of the piston again, you can say, well, you've got this expanded, cool parcel in the piston. Now, when the piston comes back down again, it will compress the molecules so they have less space to move in. As they have less space to move in, they make more collisions. As they make more collisions, they transfer energy among themselves. As they transfer energy among themselves and from the walls, that means the temperature of the molecules increases. So you have a compacted, a compressed, warm parcel at this point. So that's just a review for you on that. When we look into this, we look into atmospheres now that are constantly undergoing expansional cooling and compressional warming. Talk about the atmosphere, we're always talking about equilibrium and seeking equilibrium. We've talked about equilibrium for energy. Sometimes when we talk about that equilibrium for energy, we're talking about temperature. Here, we start to talk about equilibrium of energy as it relates to movement in the atmosphere. The atmosphere will always be supporting movement up and down for parcel. And the atmosphere will always seek a balance point of that movement. There are different types of equilibrium for that movement. You are seeing here not much movement in the atmosphere. In other words, the atmosphere has a lid on it here that is preventing cloud development. This cloud is trying to move up, it's also moving down, and it is staying at a stable altitude. When you look at this smog level, this parcel of smog is trying to move up. It is being balanced by another parcel that is moving down, and we aren't getting much movement in this atmosphere at all. What you're seeing here is a plume from a smokestack, and it is moving in a very horizontal nature. So this plume, which is warm coming from a smokestack, should be rising, but it is being pushed down into place by another air parcel above it. So we aren't getting that much movement in these atmospheres that you see here. This is what we call a stagnant situation for the atmosphere, and we think of this as a stable atmosphere. Stability describes the characteristics of the atmosphere. These atmospheres without much movement are called stable atmospheres. On the other hand, you can look at atmospheres that had very fierce updrafts and downdrafts. You see it here. The hallmark of an unstable atmosphere with huge updrafts, and the downdrafts are over here in the blue sky around it, fierce downdrafts, is that unstable atmospheres break through the stratosphere lid. In other words, this cloud has so much energy to it that it can break through the higher temperatures of the stratosphere just a bit, because the latent energy that is being released here is so warm that it can break through the stratospheric layer that you see near the downdraft sides. The center has more energy. The downdraft sides have less energy and support the downdraft. So these are called unstoppable atmospheres because the stratosphere couldn't even stop it. And we think of these as being in unstable equilibriums of updrafts and downdrafts. What you're seeing here is you are seeing just a touch in here of the rise above the stratosphere. You are seeing in here a touch above here of a rise above the stratosphere. In a more sedate representation, you might see a smokestack that has a rising plume. In other words, the plume doesn't go out horizontal. This is a rising plume that keeps rising and rising. The sign of an unstable atmosphere. It is not as unstable as this atmosphere, but we will learn about how to measure and calculate the amount of instability in the atmosphere. Obviously, you can see how important that is to predicting violent storms. Again, stability describes the characteristics of the atmosphere. These are unstable atmospheres. Now let's compare. We can have in the same location, we can have an stable atmosphere and an unstable atmosphere on different days generally. With the western fires moving east, we've noticed a lot of haze in weeks past. Now when we look outside, the atmosphere has cleared out. Previously with the haze, we had a stable atmospheric event, and then we moved into an unstable atmosphere event. This can happen over the course of a few days, and when pilots look at this, they look at the clouds as messengers to them along like signposts along a highway. When pilots see good visibility, like they see in here, and cumulus cloud formation, these are cumulus clouds, just starting their vertical development, then they know that they might be facing turbulence ahead. This is an atmosphere with stronger updrafts and stronger downdrafts. So they can anticipate, maybe they put the seatbelt sign on when they're moving into this type of an atmosphere, an unstable air atmosphere. But on the other hand, the visibility is great, so people wonder, why do I have to put my seatbelt on? When pilots see poor visibility in haze or in smoke, they anticipate that they will have a smooth ride and they can turn off the seatbelt sign. They might run into stratiform clouds, stratus layered clouds that might hamper their visibility, and they may run into continuous precipitation, but they won't run into turbulence and updrafts and downdrafts. So this is how pilots use the stable and unstable atmospheres, and they go by their observations here. So we are going to start chapter 5 by evaluating atmospheric stability, not only on the observations that we can make right outside our window, but on the observations and data that we can collect from soundings. So I'll see you on the next video applying data from soundings to the observations that we make about clouds.